I am recording. All right, so we have a nice oven. Oven has some coils. These are my coils in case my drawing is too horrible. Maybe we send some current through these coils. Our input here will be the current that we put through our coils. We'll call that I of T. This is our current. And then what do you think our output is? What do we care about with an oven? Temperature, yeah, that's the thing that we care about. We'll call that T of T, and this will be our output. All right. If you've taken heat transfer or maybe thermodynamics, you might be able to derive the following differential equation. What do you think T-amb is?
Ambient temperature.
Yep. So the rate of change of the temperature in the oven is a function of the difference in temperature between the oven and the outside temp, plus I of T. All right. Is this a first order differential equation? Wait, someone said maybe no? It is. It is a first order differential equation. Great. Because we only go up to one derivative here on the temperature term. My next question for you, is it LTI?
No. Yeah, it's
A little bit of confusion, and understandably so. It is actually not LTI. Does anyone know why? Yep.
because the current changes with time.
Not necessarily. So remember, both the input and the output are allowed to change with time, but it's the parameters, the coefficients of those that need to not change in time. Let's distribute the K term and look at what happens. We have a K times T ambient minus K temperature of the oven plus I of T. Okay, so we have our input and our output, and then we have this term here. Is this term changing in time? No, it's just a constant, right? We assume that the ambient temperature is something that is not affected by our oven. In all actuality, it probably is affected a little bit. But we assume that it is not. So T ambient is constant. Our constant K doesn't change. So we have a constant term. So what do we call a function that looks like this as opposed to this? Anyone know? What? Yep, so if we have a constant b, we call this an affine function. Affine. This is a linear function, which is kind of crazy, right? The equation that we make for a line is not actually a linear function. To be LTI, to be a linear function, the function must cross through 0, 0. Otherwise, it is an affine function. However, we can turn it into a linear function quite easily with a simple change of variables. Okay, so what I'm going to do is I'm going to make a new T tilde term. Sorry, just going to say change of variables. I'm going to say T tilde is equal to T minus T ambient. If I do this, what is my T tilde dot? Yep, Martin?
T dot plus, or it's just T dot?
It's just T dot, yeah. Yep, because that T ambient is not changing. Okay, so let's plug this into my differential equation here. So we said this T dot is just equal to T tilde. Those are the same exact thing. Equals K times T tilde or negative T tilde. It's negative T tilde. Plus I. Do I now have that y-intercept term? Do I have that affine nature? No. Nope. I'm now LTI. We got rid of the affine term. Okay, good. So now that I'm LTI, what can I find about this system?
Transfer function.
Yep, beautiful. Let's find our transfer function. Okay, so I already have capital T's, so I'm going to write my extra capital T's like this. That'll be my extra capital. Yeah, Leland?
I'm wondering why is KT tilde LTI but KT isn't?
So this is not the problem.
Oh,
This is the problem
oh, okay.
because it's an addition of a constant term. That's what makes it
Oh, yeah, okay.
affine.
Got that.
Yep. So this is absolutely linear. You're correct. Yep. Great question. Okay, let's find the transfer function. So I should have an S times extra capital T tilde. What do I assume about my initial conditions?
0.
They're 0, right? So I don't have any extra add-on to this. So that's the entire left-hand side. I have minus K extra capital T tilde plus big I of S. All right, let's get all my T tilde terms on the left. Output is the temperature, so I want output big T tilde on top. So I needed to divide by I and then also divide by S minus K. So my transfer function here is yes, ma'am. Thank you. All right. We got our transfer function. In fact, oopsies. Let's review MATLAB a little bit. If I wanted to simulate this in MATLAB, what would I do? Alex thinks we need to use the TF. Yep, we absolutely do. But before we use TF, we probably need to define some value of K, right? So we have, let's say maybe K is 10. And we'll set a transfer function object G equal to TF of what? What are the constants of my numerator?
1 over 1, 1, 1, and then 1, 1.
Yep, so the constants of my numerator are just 1. And the constants of my denominator are what?
1K.
1K. Good. Yep. Okay. If we were to do this, we would get something that looks like this. Oh, no, I didn't simulate it yet. What do we do if we wanted to maybe give it a step input?
Is the current step input?
Step input to the
Step
current.
G?
Yep, step G. Very good. Okay, so we'd have our current off, and then we flip on the switch to the oven. Does the oven instantaneously go to our desired temperature? Of course it does. No, it doesn't. It takes some time. It takes a little time. So we have some desired temperature up here, and it slowly raises to that temperature depending on a lot of different properties of the oven. So we have a constant current. We turn it on. And this is equivalent to a step input. What is the transfer function, or sorry, not the transfer function. What is the Laplace transform of a step function?
1/s.
1/s, yep. Very good. It turns out for first order systems, they all have this very similar behavior of this kind of exponential either increase or exponential decay. Do they boing, yoing, 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 yoing? Nope, they don't do that. Only what order? What order does that?
Second order.
Second order and above, yes. So first order systems actually only have really one property about them that completely defines their behavior. What? No. So what is, maybe what do you care about in your oven? When you turn it on, what behavior would you like to happen?
Stability.
Okay, yes, I would love for my oven not to increase in temp until my house burns down. That's true. I do care about stability, but there's also another behavior. If I am maybe wanting to make dinner, would I prefer that I'm able to make dinner within the next half hour, or would I maybe, the what? The time it takes for it to heat up, yes. So these first order systems can be completely described by their time constant, which refers to how fast they respond. Okay, so let's say I'm curious about this system's time response. Which is how long it took to heat up. And so to understand this property of our system, we really only need one number called the time constant, which is defined as the time it takes to get, I'm gonna let you guys tell me that. Blank percent of the way to the steady state value. If you can tell me this number, I know you read the book.
2/3.
What is it?
This is like 2/3.
Nope. Conrad?
Point 7.
You're close, but no.
67?
Even closer, but no. Adne?
1/e or something?
Okay, you're getting very close. It is actually 1 minus 1/e, which is 63.2% of the way there.
It's basically 2/3.
Okay. So if we wanted to, we could, even just looking at our response of our system on our MATLAB plot, we could say, okay, what is this steady state value that it's approaching? We could take our cursor along this function here, and we could find the point where it gets 63.2% of the way there. And that would be the time constant of this system. But we can also calculate it. And for that, we're going to do a different example here. So I can find this on the MATLAB plot. What do you think it'll depend on?
The value it approaches.
Yes, the value that it approaches to some degree.
The current in K.
The current in K, yeah. But even more so, what do I have in my transfer function? Poles and zeros. What variable in my transfer function sets my pole?
Okay.
K. Yeah, it depends on K. Now, K in this system is a property of the actual materials involved. That's it's set by the environment. But in other systems, K will be a value that we can choose. And so in that case, we call that our control gain. And we can set K to give us a desired time constant. Okay? So let's see. This property depends on K. And when we have control gains, we can set K to give us a desired time constant. And this is a really important idea that we will come back to a little bit later in this course. Okay, so let's look at a much broader sense of a transfer function. So we're not going to look at an exact system here. Let's look at the form of a transfer function. I can write a transfer function as the output C over the input R, or I can give it a variable G, or I can write it as a polynomial in the numerator over a polynomial in the denominator. So I'm going to write it that way. I'm going to make all my constants in the numerator B's. And I'll make all the constants in the denominator A's. Bless you. Is that the only way that I like to look at transfer functions? Do I like to look at it as polynomials, or do I like to maybe rearrange it a little bit? Yes, we like to factor into multiplied terms. So another very broad general way of writing a transfer function is to say S plus Z1, S plus Z2, however many terms you need depending on the order of your system, over S plus P1, S plus P2, Okay, why do you think I chose Z's in the numerator and P's in the denominator? They stand for poles and zeros. Yes. The negative Z's are zeros. These are values that cause the numerator to become what? 0. And the negative p's are poles. Values that cause the denominator to become 0. Okay, in our oven example, you pointed out and said that K value is setting the pole, and that K value also determined how my system responds over time. And that's a common theme. Those poles, those values that cause this denominator to become 0, those are what set the behavior of your system through time. Okay? So regardless of what transfer function you're looking at, poles are always important. All right, let's make this concrete with an example. Let's say I have a system that looks like this. What are my poles? What's my pole here? -5, very good. What's my 0? -2. Very good. Are poles and zeros always real numbers? No. When we have roots of a polynomial, they could also be complex. So something that we often will do is to plot these poles and zeros on what we call the S-plane or the imaginary plane. So we can plot our poles and zeros on the S-plane, where our horizontal axis is going to be the real part. The vertical axis is the imaginary part. You might also see this as sigma on the horizontal axis and j omega on the vertical axis. And the reason we write it this way is we give our poles and zeros the form sigma plus j omega. All right, so the sigma is always the real portion of that root, and the j omega is the imaginary portion of that root. All right, if I want to plot my pole, what symbol do I give poles usually? Do we know? I usually give poles an X. Okay, so do I have any imaginary part in my pole here? No, so I need to be on the real axis at -5. What symbol do you think I give zeros? Either an O or a 0. Yep. If I wanted to generate this plot using MATLAB, what would I use? PZMAT, very good. Was that Martin? In MATLAB, I could have said PZMap of my transfer function g if I had named this g. Very good. Okay, you'll notice that I specifically referred to a step function when I was talking about my oven. And I did that very particularly. We always define our time constant with respect to a step input. So for all of today's chapter, we're going to assume that we've given our system a step input. Okay, so let's give g, our transfer function, a step input. If I wanted to calculate the response of my system to that step input, what kind of math should I do? How do I figure out that system response to a step input? Well, tell me about the definition of a transfer function. Transfer function is what over what? Yep. Okay. So I have output over input is equal to S plus 2 over S plus 5. Do I know my input? Do I know my input? So G is the transfer function as a whole. I said we wanted to give it a step input. What is the Laplace transform of a step input? 1 over S, right. So that means that big R of S equals 1 over S. So I know C over R, and I'm going to give it an R, and I want to calculate the output. What should I do? Should I subtract them? Should I add them? Should I multiply them, divide them, Haley? I should multiply them. Yeah, if I have a C over R and I multiply it by an R, I get C. Easy peasy. So let's do C of S is equal to, how do I want to write this? I'll just go ahead and write it. S plus 2 over S times S plus 5. There we go. Great, now what? What if I want to know the time domain response to this step input? What should I do to this thing that I have here? Inverse Laplace transform, absolutely. All right, that looks something like this. C of t is equal to 2/5 plus 3/5 e to the minus 5t. Okay, interesting. Very interesting. Tell me about this 5. Where did this 5 come from? That was our pole, okay? So our pole set how quickly this exponential decay happens. So the pole sets the speed of that exponential decay. Tell me about what happens here. Why did we have this term? That's because of the 1 over S, yes. This portion is called the forced response. This portion is called the natural response. Okay, so the exponential decay here would have happened regardless of what we did to the system. If we had not given it a step input, we would still have this exponential decay. But the 2/5 is specifically because we gave it a step input. Okay, let's look at maybe what happens when t goes to infinity. What happens when t goes to infinity? Any ideas? Mm-hmm. Yep, so e to the negative infinity equals 0. So this decay term will go to 0. Will the 2/5 ever become 0? Yes, so that is our steady state response. Okay, so we have a system. What happens at t equals 0? When t equals 0, e to the 0 is what? 1. So c of 0 is equal to 2/5 plus 3/5. All right. So we start out at some value up here of 2/5 plus 3/5, which is 1. I start out here, and then I decay over time exponentially, but I never go back to 0. I end up at 2/5. So my response looks something like this. All right, what would happen if our pole was positive 5 instead of negative 5? Would it be doing exponential decay? No, it would be doing exponential growth. I would still start at the same point here, but instead of decaying, I do something like this. Is that usually good or is that usually bad? That is usually very bad. That has made our system unstable. Okay. Oh, sorry. What would happen? If our pole was positive 5 of negative 5. That's John Hodo telling me that my oven is going to burn my house down. This is another very, very key idea here in controls. Poles that are on the right half plane of the S-plane, so poles with positive real parts, always very bad, always unstable. Poles in the right half plane, bad. Okay, so I said I want you to remember one thing from this class 5 years from now. What was it?
State space.
State space form. This is the second thing I want you to remember 5 years from now. Right half plane poles, bad. Okay, two things. I'm going to come and find you in 5 years. No, I'm not. That'd be creepy. I'm going to come find you in 5 years and ask you about. All right. Let's do another example here. Let's consider a general first order system that is LTI. We'll write it like this. We'll say, okay, with a first order system, I only get one pole. Otherwise, I'm multiplying an S times an S, and I'm not going to be first order anymore. So I can have something in the numerator, maybe a constant, and something in the denominator that's just a single pole. We'll call this G of S. We have some output C of S. So C of S over R of S equals A over S plus A equals G. So C of S is equal to G times R. And again, for this chapter, we always assume step input. Which means that this has got to be 1 over S. So if we multiply that out, we should have A over S, S plus A. Which means our time series response is 1 minus e to the minus a t. This term is always going to be the forced response. This term is always going to be the natural response. And there are 3 properties that we will define for these types of systems. We already said one of them. What was it? Time constant. We'll say this is the time for the step response. To reach 63.2% of its final value. And we even define its own variable. We call it tau. Tau is equal to 1 over A. 1 over our pole. The next property is really just a variation of the same property. All 3 properties are just variations on the time constant, but they do define slightly different behaviors or properties of the response. So we also have settling time and response time, or rise time. So the rise time is the time for the step response to rise from 10% to 90% of the final value. And we call that T sub R, and it's equal to 2.2 over A, or 2.2 times our time constant tau. Last definition, settling time. So the first 2 properties had to deal with that initial response of the system, that early time behavior. What do you think the settling time has to do with? The long time behavior. So how does this thing behave as time extends into infinity? So the time for the step response to reach and stay within 2% of the final value. When we go to look at higher order systems, like our spring systems, is it possible that a system might never settle? Yes, absolutely. So it is very possible that a higher order system, not a first order system, but a higher order system could oscillate indefinitely so that it never stays within this 2% envelope. Okay, but our first order systems are much simpler and they behave a little bit, they behave better. All right, so we give our settling time T sub S, and it is 4 over A, or 4 tau. All right, so if I were to give you a transfer function G equals 2 over S plus 2, what is my A in this transfer function? 2? Yep. And from there, I can define all other properties. So if we compare this to our form, A over S plus A must be 2 for us. So tau is then what? Tau, 1 over 2, yep. What are my units? It's a time. Yep, it's a time. So this is 1/2 seconds. What is my rise time?
2.
Nope. My time constant was,
4 tau.
that's my settling time. Did I say settling time? I'm,
No, you're right.
rise time. Yep. 2.2 over 2, or 1.1. And then my settling time, TS, equals 4 over 2 equals 2. What would happen if I multiplied by a constant? Would it change any of my time properties?
No.
No, what would it potentially change?
Value is so flat.
The value that it settles at, right? So if I were to say maybe G, what if I have a transfer function that is a little bit harder to make it look like our formula here? What if it were maybe G equals 1 over S plus 2? I don't have the A in the top and the A in the bottom. They're different. What can I do? I can multiply.
By 2 over 2.
I'm going to multiply by 1/2. This would be, I can say, let's do 1/2 times 2 over S plus 2. Is that the same thing?
That's what you're saying.
Yeah. Are these the same thing? Yeah, they're the same thing. Now this one looks like the form I'm used to seeing. I have the A over S plus A, but I've multiplied by a constant 1/2. Right? It doesn't change any of my time properties. Doesn't change how fast things happen. It just changes where I settle at. So whoops. actually. They would start the same. I'm just gonna make a note. Doesn't change any time properties. Okay. All right, that's all I'm gonna say about first order systems. I finished a little early today, but that's okay. I don't wanna get into second order until we have the whole day on second order. So, have a great weekend. I will see you guys next week. Let's check. I believe next week we have potentially some items due. Yes. Proposal is coming up. Keep an eye on the due dates for the proposal. What? I'd prefer the proposals be submitted on PDF, but if you want to turn them in class, you can. No, it's on the PDF. This is me talking to you about the proposal. The proposal is going to be due soon. There is a document online that tells you exactly what I want out of your proposal. Hooray. If you have any questions, let me know.
I just missed something. That's the name of the document.
I did that? Oh, Pretty Ponies, right, yeah. I like it. Pretty Pony proposal. Perfect proposal. Yes, ma'am.
Okay, how is it over 5 here? It should be. Oh, okay.
So I should have AS plus 5A plus BS equals S plus 2. So 1 equals B. And, oh no, A plus B. And 2 equals 5A. Is that right?
Yes.
So A is 2/5. So B has to be 3/5. Right?
So what does the S disappear to?
What do you mean?
Because you said A, so that's 2 or 5 over S, right?
Yep, so my terms would be 2/5 over S plus 3/5 over S plus 5. And then do you have your Laplace transform tables? Hi, Carla. Yeah. Got it.
Sorry.
You're fine. Yeah.
I think I'm TAing for a class, and then Dr. Larson wants me to invigilate a quiz. Would that be excused for today's lab meeting?
Sure.
I'm sorry about that.
That's okay.
And I'll update the site.
Okay, thank you. Hey, Joseph, got you. Thanks. Valeria, gotcha. Yep. Hannah Klein. I got you. Tafari, Valdez. What's up? Hi.
Do you mind sending me the Rhythm Lab template so I can start making the quick start guides off of that? On Basics.
Oh, yeah, what was I gonna send you?
You said you were gonna send me a copy of the lab intro.
Oh, yes, I need, okay. I'll do that as soon as I can.
That's all.
Cool. Thanks, Alex. Okay. Josh, attendance? Yes. I got you.
Okay, thank you.
Yep.
It's okay, he's nuts.
Hi.
I have a question about the project.
Okay.
So it says it needs to use a closed loop controller. That's different than a closed loop system, right?
No,
Okay, so there's
the
no
same.
like feedback.
there is feedback. That is the definition of the closed loop.
Oh, I'm dumb. I'm thinking of. I'm sorry.
You're fine.
I always mix them up. Okay, thank you.
All good.
Because it doesn't say the description.
Okay, so let's see. We have. I'm just gonna give us a little more space.
A little bit, so like 17 hours.
2/5 over s plus 3/5 over s plus 5. Okay, so 1 over s is
Yeah, you do what you wanna do. Don't listen
No,
to
no,
that
of course.
part.
2/5 times u
So I didn't get spoiled. And
Right.
now I'm expanding.
plus 1 over s plus 5 should be something like this. So 3/5 e to the minus 5t u of t.
So you just left out the U of T?
Yes, because I'm only talking about positive time, right? And u of t starts out at 0 at negative time, and then it goes up to 1 at t equals 0. Okay, so this is just the same as 2/5 plus 3/5 e to the minus 5t
Okay, because I was like, huh?
for t greater than 0.
Okay.
Yep,
Cool. Thank you.
you're welcome.
I was looking through it, like, wait a minute. It's not clicking in my head right now.
Yep, I just skipped all of the
Steps.
intermediate steps.
Okay, that's it. Thank you.
You're welcome.
I think that's the.
Yes, ma'am. I did. I did.
I think Team Cherry converted it.
Was that your only question?
There's a. It mentions in the game later that it is a sequel. In like one of the endings. But it is a sequel. Team Cherry already said it though. Sorry, dude. I tried launching my map.